Hello friends, welcome to my channel again, and today we will discuss design of horizontal curve on a road, and in this session we will cover guidelines given in different IRC codes. So why do we need a horizontal curve? The horizontal curve is required to effect the change in the direction in highway alignment, and this change in direction in highway alignment may be necessitated because of several reasons, either to connect the obligatory points or maybe because of some topographic reasons or to reach the destinations located in different directions. So in short, a horizontal curve is needed to provide a smooth transition between two tangent roadway sections to ensure roadway driving consistency. Before we go to the details of design, let us quickly understand the elements of a horizontal curve. Now this is the highway, and this highway is required to change the direction from this direction to this direction, and it is effected through a circular curve at the center, and this circular curve is followed and preceded by transition curve on either side. So the point from where the transition starts, that is called the tangent point, and again the point where transition ends on the other side of the curve is also called a transition point. Now this is the tangent to the curve, to the start of the curve, or you can say the straight alignment of the highway from two directions. The point where it meets, that is called the horizontal intersecting point or apex point. And it subtends angle delta here, that is total deviation angle because of the curve. Now this total deviation angle is subtended here also at the center. A part of it, theta s, is compensated by transition curve, and central part, that is delta c, is the deviation of circular curve. RC is the radius of the circular curve, and this TS is the tangent length, that is the point from tangent, the distance between tangent point and the horizontal intersecting point. So in this direction as well as in this direction, this will be equal. This ES is called the apex distance. LS is the length of transition on both sides, and LC is the length of circular curve. Now all these data are needed while laying a horizontal curve in field. The design elements for a horizontal curve are design speed, radius of circular curve, side friction factor, and superelevation. Superelevation is provided through runoff and runout distance. I will discuss these two distances a little later. But design speed is the speed for which highway is designed, and this is the main factor on which all design elements like radius of circular curve, superelevation, side distance, OHD, length of transition depends. Now design speed depends upon the category of the road and terrain of the area, and IRC has suggested 4 classification for terrain: plain, rolling, mountainous, and steep, depending upon the cross slope. If it is less than 10%, it is plain terrain. If it is more than 60%, it is steep terrain. And based on these terrain, the design speeds for rural roads are given in this table. The design speed is ruling speed as well as minimum speed. So ruling speed is the maximum speed, and there is a desirable speed, or you can say the minimum speed that should be maintained. On expressways, it is 120 in plain terrain, and 100 is a minimum design speed. And similarly, for other terrain, it is given in this table. For expressway, for national and state highways, for major district roads, other district roads, and for village roads. So as the category of the road reduces, or you can say importance of the road reduces, the design speed also reduces. Design speed for urban roads are also given in IRC code, that is 86/2018, again based on type of terrain. For urban expressway, arterial roads, subarterial roads, collector street, and local street, These are the speeds given as a design speed. A horizontal curve is represented by either radius or by its degree. And degree of the curve is defined as the central angle subtended by an arc of 30 meter. That is a standard definition of a degree of the curve. So if d is the degree, then this should be 30 meter. 30 meter length of the arc of circular curve. So d upon 30 will be equal to 360 upon 2 pi r. That means for a complete circle, this degree will be 360 degree and the circular circumference will be 2 pi r. So if you put the value of pi here, you get d is equal to 1720 upon r. That means 1 degree curve will have a radius of 1720 meter, 2 degree curve will have a radius of 860 meter, and so on. Now, in the theory of design, the basic theory is that when a vehicle travels on the horizontal curve, it experiences a force that is called centrifugal force, and this force acts outside the horizontal direction, that is outside of the curve. So if this is the vehicle, and let us say this is the center of gravity of this vehicle, we assume that the centrifugal force will act at this point on the vehicle at the center of gravity. So let us say F is the centrifugal force which is horizontal, and W is the weight of the vehicle which is acting vertical. Now the resultant of these two forces, horizontal and vertical, is R. And if B is the wheelbase of the vehicle, then this vehicle will be in stable position as long as this line of resultant force does not pass through the outside of the base. Means this red line will pass through a point on the wheelbase which is between the wheels of the vehicle. If h is the height of the center of gravity above the surface, and let us say x is the distance, horizontal distance from the vertical to the point from where this resultant force passes through, then you can say tan theta, this theta is the angle, tan theta will be x upon h. X is the horizontal distance and h is the vertical. Or you can say the limiting case will be when this red line or the resultant force passes through this point, that is the center of the outer wheel. So in that case, it will be half of the wheel base. So tan theta will be b by 2 upon h, that is b upon 2h. That would be the limiting case. If this tan theta exceeds this value, then it will create overturning of the vehicle. So overturning will be avoided as long as tan theta is less than b upon 2h. Now let us consider the same vehicle. Now here the horizontal force F is centrifugal force that is given by this equation, mv square upon r. M you can put W is the weight of the vehicle, weight upon acceleration due to gravity, W by G, V square upon R. Now if you take moment of these two forces, horizontal force and vertical force, about this point, that is center of the outer wheel, then this will be the condition, limiting condition will be that F into height of the center of gravity h should be equal to W into B by 2. That is a half of the wheelbase. So this is a limiting condition, or you can say F upon W is equal to B upon 2H. Now that is called, this F upon W is called centrifugal ratio or impact factor. And in this figure, if you see F upon W, now this is the F Okay, this is the horizontal force F. So F upon W will be tan theta. So tan theta should be equal to B upon 2H. The same equation which we derived earlier can be derived through moment also, forces also. So overturning will be avoided as long as this impact factor F upon W, or you can say B square upon R into G, is less than or equal to B upon 2H. Now, centrifugal force will cause more pressure on outer wheel and low pressure on inner wheel. That means if RB is the reaction at outer wheel and RA is the reaction at inner wheel of the vehicle, then RB will be more than RA because of this horizontal force. Now, this is registered by the friction between the tire and the pavement. So, this F, if there is no superelevation, if the vehicle is allowed to move on flat surface, then this F should be equal to small f is the coefficient of friction, Ra plus Rb. And this Ra plus Rb naturally will be equal to weight of the vehicle, and therefore F should be equal to F into W, or you can say that centrifugal force or impact factor should be equal to F. So if there is no superelevation, then safety is fully dependent on friction force, friction between the tire and the pavement. And it says that when centrifugal ratio attains a value equal to the coefficient of lateral friction, there is a danger of overturning. So if F is less than B upon 2H, the vehicle will skid, but it will not overturn. But if F is more than B upon 2H, the vehicle will overturn on the outer side before skidding. Now, to counter the effect of the superelevation and to keep the pressure on two wheels equal, we raise the outer edge of the pavement with respect to the inner edge, and that is called the superelevation. The basic objective of providing superelevation is to counter the effect of centrifugal force. And for that, we introduce centripetal force by tilting the vehicle by a certain amount like this. So if you tilt the vehicle and you provide pavement in this manner, or you can say you tilt the pavement and place the vehicle so that it is tilted on a horizontal curve, so that a part of gravity is acting towards the center of the horizontal curve. So if you take this figure, this is the pavement now, which is tilted at angle theta, and let us say capital B is the pavement width, and total tilt here, total rise of the outer edge with respect to the inner edge is capital E. For no radial acceleration, outward and inward forces must be balanced. Okay, so if this is the angle theta, that is the tilt, this angle theta will be reflected here also, then tan theta will be equal to sine, because theta is very small, you can take tan theta equal to sine theta, and it will be E upon the pavement width, B, capital B. And that is what we call the superelevation. That is the ratio of relative elevation of outer edge to the pavement width. And this will be naturally, this superelevation will be, total superelevation will be, capital E will be E into B. E is the rate of superelevation. Small e is the rate of superelevation. Now, as I told you, for no radial acceleration, no unbalanced force, outer and inward forces must be balanced. So what is the outward force? Now, with the tilted pavement, the outer force, F is the outer force and W is the gravity. Now these are resolved parallel to the pavement and perpendicular to the pavement. So if you resolve F parallel to pavement, its component will be F cos theta, and this vertical component component means perpendicular to the pavement will be F sine theta. Similarly, the weight of the vehicle will have two components now. One is W cos theta, that is normal to pavement, and a component parallel to the pavement will be W sine theta. Now the effect of this F sine theta is to increase the pressure on two wheels because it is now normal to the pavement. So outer force is F cos theta, inward force is W sine theta, that is the component of the weight of the vehicle normal to the pavement, plus frictional force between tire and the pavement. Now this frictional force here will act opposite to the skidding. It will basically resist the skidding of the vehicles. So inward force will be W sine theta plus coefficient of friction into the weight normal to the pavement, that is W cos theta plus F sine theta. And if there is no unbalanced force on the vehicle, then these two outward and inward forces must be equal. So F cos theta should be equal to W sine theta plus F into W cos theta plus F sine theta. Small f here is the coefficient of friction in lateral direction. Its value is generally 0.15. So if you simplify this equation, it becomes that F upon W into 1 minus F tan theta is equal to tan theta plus F. Now here in this equation, F tan theta is very small because the minimum value of F we take 0.15 and tan theta maximum value we take 0.07, and therefore this F tan theta will take a value of 0.01, or you can say 1 minus F tan theta will be almost 1. So this equation reduces to this equation, F upon W is equal to E plus F. So this is the equation which will correlate superelevation and coefficient of friction with speed and radius of the circular curve. Now in this equation, E is the rate of superelevation, F is the design value of lateral coefficient of friction, which is generally 0.15, V is speed in meter per second, R is the radius of circular curve in meter, and G acceleration due to gravity. Its value is also 9.8 meter per second square. Now if we take speed in kilometer per hour, then this equation becomes V square upon 127 R. And as I told you, maximum value of E is 0.07 and minimum value of F is 0.15. Therefore, the contribution of friction force in countering the effect of centrifugal force and providing the stability to the vehicle on horizontal curve is much higher than the contribution of superelevation alone. You can see here it is just 0.07, it is double of that, 0.15. And there can be many situations in field when superelevation is not feasible or not desirable to provide. And in that case, side friction takes care of total centrifugal force. Now, this situation can be on a roundabout. On a roundabout, when vehicles move around the center island, they require that the outer edge of the curve must be higher than the inner edge. But from drainage point of view, we provide this side higher than the outer edge of the circle. And therefore, the camber, whatever camber is provided on a roundabout, that acts as a negative superelevation for all vehicles. And this is basically the vehicles here do not overturn or do not skid because the speed is very low. The speed is very low. Similarly is the case at intersections. When at intersection, a vehicle makes a right turn, it requires that it should have certain superelevation in this direction. But on the same intersection, when this vehicle makes a right turn, this requires that there should be a higher elevation on this direction. So requirements are conflicting, and therefore this total conflict area is kept flat, and we do not provide any super elevation in the central area. Only slope which is required for drainage purpose, that is provided. The coefficient of side friction depends upon the speed. At low speed it is very high, at high speed it is very low, and therefore at roundabouts or at intersections, because speeds are low, the coefficient of friction is high, and therefore the vehicle is safe. Now in this equation, if you look at this equation, E plus F is equal to V square upon 127 R. Now for a given value of F that we assume 0.15, this super elevation will depend upon speed and radius of circular curve. Now radius of circular curve is also decided based on the geometry of the road, depending upon the alignment, and therefore E will be directly proportional to the speed. So more speed means more requirement of super elevation. Now if you design a horizontal curve, we take V at design speed. But if actual speed of the vehicle is more than design speed, then the super elevation which is provided remains deficient because requirement is more. And similarly, when the actual speed of the vehicle is lower than the design speed, then super elevation will be in excess. Now this excess super elevation will create unnecessary tilt of the vehicle, and it will also create more pressure on inner wheels than on outer wheel. Similarly, deficit super elevation will cause unbalanced portion of centrifugal force, and pressure on outer wheels will be greater than that on the inner wheel, and that will cause very fast deterioration of outer edge of the pavement. Because super elevation cannot be increased indefinitely, and therefore a maximum value of super elevation is recommended by IRC code. For plain and rolling terrain and snowbound area, maximum value is 0.07, that is 7%. And for hill roads which are not bound by snow, its maximum value is 0.1, and in urban road it is limited to 4% only. And the minimum value of super elevation should be equal to the camber. So when you design a horizontal curve and when you calculate super elevation, if it is coming less than camber, then we provide super elevation equal to the camber. Now, as I told you, E depends upon the speed and radius. So if radius is very large, then centrifugal force will be very low and normal camber can be retained, and there is no need to provide any super elevation. But remember, the camber will act as negative super elevation in the outer part of the carriageway. So IRC suggests that there is no need to provide super elevation under these conditions as given in this table. When design speed is 20, let us say 20 to 100 km per hour, and camber, suggested camber is 4%, 3%, 2.5%, 2%, 1.7%, then for these values of radius, there is no need to provide any super elevation. If radius exceeds these values corresponding to a particular speed and corresponding to particular camber, then there is no need to provide any super elevation in the field. So what is the design procedure now? Design procedure is that first we calculate super elevation for 75% of design speed. So we assume that this super elevation will take care of centrifugal force corresponding to 75% of the design speed. So if you put in this equation 0.75 into V square upon 127 R, it becomes V square upon 225 R. V is in kilometer per hour. If this E calculated is less than 0.07, provide E as calculated. If it is coming more than 0.07, then restrict to 0.07 and then we check for F. Now F is given by this equation, that V square upon 127R minus E. So you calculate what is the value of F here for given value of V, R and E calculated above. If this F is coming less than 0.15, design is safe. If it is coming more than 0.15, that means requirement of F is more than 0.15, then we restrict the speed because that design is not safe. In that case, you calculate what is the allowable speed on that particular curve, VA. So take maximum value of 0.07, take maximum value of 0.15, which is permissible, and calculate what is the allowable speed, VA, using this equation. So this gives you VA is equal to square root of 27.9 into R. That would be the permissible limit of speed, and we restrict this speed through the speed limit sign before and after start of the curve. After you design superelevation, the next step is how to attain this in field. And introduction of superelevation on a horizontal curve in the field is an important part of construction. The full superelevation must be provided at the start of circular curve, and this transition length helps in achieving it. This superelevation is provided in two steps. The first step is to eliminate the crown of the cambered section, and second step is rotate the pavement cross section to attain full superelevation. Now, elimination of crown of the cambered section can also be done in two ways. The first method is that outer half of the camber is rotated about the crown at the desired rate such that the surface falls on the same plane as the inner half. So this becomes equal to the camber. The slope becomes equal to the camber. And in the second method, this crown is progressively shifted towards outside. Now this method has some complications and therefore it is not usually adopted. This is the most commonly adopted method, where the outer edge is slowly, progressively raised so that this crown is completely eliminated and the slope here of the pavement becomes equal to the camber. You see, now this is the cambered section, that is the starting point of transition curve, and then in this distance, in this length of the road, this camber is flattened here in the outer part of the center line of the curve. Now this distance is required. This distance which is required to make this outer portion of the camber flat, that is called runout distance. And then slowly this is again raised so that here you get the superelevation, full superelevation. Now runout distance is length required to make outer lane flat, and runoff distance is length required to achieve full superelevation. And this is called the total transition length, runout distance plus runoff distance. It is explained in this figure. As I told you, before the start of the circular curve, there should be full superelevation available. The step 2 is to provide superelevation, and this can be done in three methods: by revolving the pavement around the center line, or by revolving the pavement about the inner edge, or by revolving the pavement about the outer edge. And each of these methods has some positive and negative points. In first method, rotation about center line, the superelevation is achieved by depressing the inner edge and by raising the outer edge, each by half the total amount of superelevation. Now in this method, the vertical profile of the pavement remains unchanged. Outer edge is raised and inner edge is lowered or depressed, and it also results in somewhat balancing of earthwork. Now since we are depressing the inner edge here, so drainage sometimes becomes a problem when you attain the full superelevation by this method. In the second method, the rotation of the pavement is done about the outer edge. So here the inner edge remains at its position and full superelevation is provided by raising the outer edge. Now it is preferred in flat terrain in high rainfall area to avoid the drainage problem. But here you must note that the entire pavement including outer shoulder is to be raised, and that is the disadvantage of this method. Sometimes it becomes uneconomical also. The third method, where we revolve the pavement about the inner edge, is not used in field because that creates serious problem of drainage. So that is how superelevation is attained in field. Let us now take one example to illustrate the procedure of determining superelevation on a road. And the question is, determine the amount of superelevation to be provided on a horizontal curve of 450-meter radius encountered on a national highway having a design speed of 90 km/h. So solution now, given data is design speed is 90 km/h and radius is 450 meter. So first we calculate superelevation for 75% of design speed using this equation. E is equal to V square upon 225 R. That comes out to be 0.08. Now this is more than 0.07 and therefore we provide maximum value of E equal to 0.07. Now with this value of E, we check for side friction value. F is equal to V square upon 127 R minus E, and if you put the value of V here 90 km/h and E 0.07, radius 450, it gives you 0.072. Now this value is less than 0.15 and therefore design is safe. Therefore we provide superelevation equal to 0.07. So thank you very much for watching this video. If you have liked, please share with your friends and write your comments in the comment box.